Hi, good morning, everyone. Good morning. People online, hello, can you hear me? Hello, hi. Hello. People online, hello, are you there? Can you hear me? Hi. Hello. Yes. Okay, hold on. Give me a minute. Right, okay. Question 15 is a homework, is it? Question number 15. In 1931, Sloan and Lawrence built a linear accelerator with several drift tubes. Several drift tubes. They used LINAC 2. We'll do this question later. Have you done this already? We'll do this question later. We'll come back to this. Right on the next topic. You have already written the subtopic, I guess. EMF induced in a coil. Is it? Induced in a coil. Correct. Okay. Let's draw this diagram. There's a magnet, bar magnet, and there's a coil next to it, and an ammeter is connected to the coil. Okay. Right. Guys, you know from your O levels, when you take a magnet and move it towards or away from a coil, there will be an EMF induced in the coil. Have you learned that for O levels? Yes. When you take a magnet and move it towards coil, towards and away from a coil while you keep it moving, there will be an EMF induced in the coil. So you will get to see that in this, if you do a simple experiment, taking a coil attached to a ammeter and a magnet which is moved closer. If you keep moving the magnet, there will be an ammeter reading. Correct? Agreed? Did you know that? So there are two ways that you can do. Is either you can keep the coil stationary and move the magnet, or you can just keep the magnet stationary and move the coil towards and away from the magnet. In either cases, there will be an EMF induced in the coil, so there will be a current in the coil. Correct? So now let's say you keep the coil stationary and you move the magnet towards and away. So if you're moving the magnet towards the coil, the EMF induced here will be in one direction, so the current will be in one direction. When you're moving the magnet away from the coil, the EMF induced will be in the opposite direction, so the current in the coil will be in the opposite direction. Okay. So if you're moving the magnet towards and away from the coil, the direction of the current in the coil will keep on changing its direction. Right? And the other thing is, when you move this magnet faster, if you move it faster, the current here will be what? Greater. The reason? The EMF induced will be greater. So that is explained in what law? Faraday's law. You have done this 4 levels. Okay. Faraday's law, which says the EMF induced in a coil or EMF induced is directly proportional to the rate at which the magnetic field lines are cut. So the reason why there is an EMF induced is that now there are magnetic field lines. So now, sorry, the opposite direction. There are magnetic field lines, right? So when you move this magnet or when you move the coil, these magnetic field lines get cut by this coil. So when the magnetic field lines get cut by the coil, there will be an EMF induced. Okay. So Faraday's law explains that the EMF induced is proportional to the rate at which the magnetic field lines are cut. Okay, right under that. When the magnet is moved towards, or away from the coil, when the magnet is moved towards or away from the coil, there will be a current in the ammeter. There will be a current in the ammeter. Full stop. Even if the coil is moved towards or away from the magnet, even if the coil is moved towards or away from the magnet, even if the coil is moved towards or away from the magnet, there will be a current in the ammeter. There will be a current in the ammeter. Full stop. It is because of the EMF induced across the coil. It is because of the EMF induced across the coil. Okay. Right below that. This induced EMF this induced EMF can be increased by making the following changes. Under that, in point forms. The first one, moving the magnet or coil faster. The next one, using a stronger magnet. And using a coil with higher number of turns. So guys, by making these changes, you can increase the induced EMF. One is moving the magnet or the coil faster, or using a stronger magnet, or using a coil with high number of turns. If you make these changes, you can get a higher EMF induced. Okay. So this is what explained in Faraday's law, which is about the EMF induced, the magnitude, right under that. The next subtopic. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Right? The EMF induced is directly proportional. The EMF induced is directly proportional to the rate of change of the EMF induced is directly proportional to the rate of change of magnetic flux linkage. To the rate of change of magnetic flux linkage. Okay. Right. Right on the next subtopic. Inducing. Oh, hold on. Guys, write down this equation. Oh, wait. That is all. Right on the next subtopic. Inducing an EMF. In a coil using another coil. Inducing an EMF in a coil in another coil using another coil. Inducing an EMF in a coil using another coil. Right. First draw this diagram. Look at this. So there is a coil here and another coil here, and they are winded around an iron core. There is an iron core in the middle, and the two coils are winded around that. And this coil, I'll label it A, and this coil is labeled B. And here there is a switch in the coil A, and there is a alternating current supplier, alternating power supplier connected to the coil A. On the coil B, there is just an ammeter. Draw the diagram. Done. Right on the net. When the switch in the coil A is closed, when the switch in the coil A is closed, when the switch in the coil A is closed, there will be a current in the coil A. There will be a current in the coil A. And there will be an EMF induced through the coil. See your page. There will be a current in the coil A, and there will be an EMF induced through the coil. Full stop. Since it is connected to coil B, through an iron core, there will be a magnetic field. There will be a magnetic field. There will be a magnetic field through coil B as well. Through coil B as well. Okay. There will be a magnetic field through coil B as well. Right, guys, now listen to me. Now you know you have done these 4 levels. You have heard of transformers, right? Transformers are used for what? Transformers are used for what? Huh? To increase the temperature? To increase or decrease voltage? Yes. There are 2 types of transformers. What are those? Step up and step down transformers. What happens in a step up transformer? Voltage is increased. In a step down transformer, voltage is decreased. In a step up transformer, you remember the number of turns in the secondary coil is more than the number of turns in the primary coil. In a step down transformer, the number of turns in the secondary coil is less than the number of turns in the primary coil. Did you all straight away come from grade 6 to A levels without doing any? Anyone who hasn't done this for levels? You have done it, right? For local levels, we have done. Okay, listen. So there are step up and step down transformers. Now listen, guys. So the idea behind step up and step down transformers is this. Now there are two coils. So using this, we can call this the primary coil, and this is the secondary coil. So how does it work? Listen. So now if you supply a voltage, if you supply a current to this coil A, when a current is passing through coil A, there will be magnetic field induced through that. Okay, according to right-hand grip rule, there will be so because of the current in there will be a magnetic field passing through the coil A. So that magnetic field which is induced will go through. It is connected to the coil B as well by the iron core. This magnetic field will pass through the coil B as well. Okay. Due to the current in A, there is a magnetic field induced, and that magnetic field induced will pass through the coil B as well. Then that magnetic field, which is increasing in strength or decreasing in strength, change in the magnetic flux linkage through the coil B. So there will be an EMF induced in coil B. I repeat, listen. Now you are making a current pass through A. You close the switch, there will be a current passing through A. So that current passing through A will induce a magnetic field through this coil A. That magnetic field lines will pass through this coil B as well. So the magnetic field lines through coil B is changing. That means the magnetic flux linkage through coil B is changing. So when there is a change in the magnetic flux linkage through coil B, there will be an EMF induced in coil B. So that means this ammeter will show a reading. Or if you put a voltmeter here, that will show the voltage. Understand? So basically, by supplying a voltage to the primary coil, you can get a voltage in the secondary coil. This is the idea behind the transformer. Okay. But the question is, now let's say, now here I have indicated it's a alternating voltage. No? What if I just give a direct current? If I just use a battery, and if I give a direct current, do you think there will be an EMF induced here? There won't be. Why? Because if the current is constant, listen, the current is constant means the magnetic field induced will be constant. The magnetic field induced is constant means the amount of magnetic field lines passing through this coil B will be constant. So that means the magnetic flux linkage through the coil B will be constant. It won't be changing. Okay. So Faraday's law says what? The EMF induced is proportional to the rate of change of magnetic flux linkage. So if there to be an EMF induced in coil B, there should be a what? Change in the flux linkage. Okay. If the flux linkage through the coil B is not going to change, there won't be an EMF induced. So by using a direct current in the coil A, you can't induce the EMF in the coil B. Okay. So that is the reason transformers only work with alternating voltages, not with direct voltages. With symbol. This one. Yeah. Alternating power supply. Okay. Right. Okay. Continue. There will be magnetic field through coil B as well. Full stop. Since the current in A is an alternating current, since the current in A is an alternating current,
Sir?
yeah.
So why did you change the link, sir? I just joined.
Yeah. Yusuf, I don't create links or I don't change links. That is not my job. It is done by the office. They send me a link. I just log in through that. That's all I do. So I have no idea what you are. Okay. Just like how you also receive a link. Tell me.
So can you go to the first page you're doing? I just want to take a screenshot.
Wait a minute. I will complete the same.
Okay.
Right. Since the current in A is an alternating current, since the current in A is an alternating current, the magnetic flux linkage through the coils will continuously change. Since the current in A is an alternating current, the magnetic flux linkage through the coils will continuously change. Full stop. So there will be an EMF induced. So there will be an EMF induced in coil B continuously. And it will be an alternating EMF. So there will be an EMF induced in coil B continuously, and it will be an alternating EMF. Full stop. Right below that. By increasing the number of turns in B, the induced EMF can be increased. Okay, right. Where's the next subtopic? Lenz's law.
So could you go to the previous page, please?
Okay. Right. Guys, this is again something you have learned here, levels. Lenz's law says about the direction of the EMF induced. So right under that. This law says about the direction of the EMF induced. This law says about the direction of the EMF induced. Right below that. EMF induced will be in such a way to oppose the change causing it. in such a way to oppose the change causing it. Right, guys, write down this equation. E equals minus delta n phi over delta t. I'll explain. What is E? The EMF induced. Delta means what? Change. N means what? Number of turns. Phi means what? Magnetic flux. So N into phi means what? Magnetic flux linkage. T means what? Time. So delta in phi means what? Delta in phi means what? Change in flux linkage. So delta in phi over delta T means what? Rate of change of flux linkage. Correct? Delta in phi over delta T means rate of change of flux linkage. What is this minus sign sitting here? That says you what? Why is it minus? Direction. It's from the Faraday's law. So the Faraday's law says, guys, the EMF induced is in such a way to oppose the change causing it. I will explain you with an example. Okay. But now just remember this minus sign says about the Faraday's, the Lenz's law, which means the EMF induces in the opposite direction to the change causing, to oppose the change causing it. Fine. Write down a question. A coil has 100 turns. A coil has 100 turns. And the magnetic flux through it a coil has 100 turns and the magnetic flux through it changes from 0 to 5 into 10 to the power minus 4 Weber. 5 into 10 to the power minus 4 Weber. Zero to 5 into 10 to the power minus 4 Weber in 20 milliseconds. Full stop. Calculate the EMF induced across the coil. Calculate the EMF induced across the coil. Right. So guys, EMF induced is equals delta n phi over delta t. So n is 100 turns. Phi is 5 into 10 to the power minus 4. This is the final flux linkage. And anyway, the initial flux linkage is 0. So the change will be just 100 into 5 into 10 to the power minus 4 because the initial is 0. Divided by the time taken for that change is 20 milliseconds. 20 into 10 to the power minus 3 to convert milliseconds to seconds. No need the minus sign. That minus sign is only to indicate that the EMF induces in the opposite direction. So when you are doing a calculation, it's just to get the value. You have to use the minus sign there. So how much is that? 2.5 volts, is it? right? Any questions? Right on the next one.
Yes, so why don't you use the minus?
Minus, here we just have to find the value of the EMF induced. The minus sign says the EMF induced is in the opposite direction to the change causing it. It is just to speak about the direction. The minus sign stands for that. So a voltage of minus 2.5 volts doesn't make any sense. Okay. So what is the EMF induced? 2.5 volts. Don't use that minus sign for the calculations. Right on the next one. A circular coil has a radius of 2.5 centimeters and 300 turns. And 300 turns. The magnetic flux density through the coil, changes from 0 to 500 millitesla. 0 to 500 millitesla. Zero to 500 millitesla in 50 milliseconds. In 50 milliseconds. Full stop. Calculate the EMF induced across the coil. Calculate the EMF induced across the coil. Can you give it a try? So guys, first you can find the cross-sectional area of the coil by using pi r square, which is pi into radius is 2.5 centimeters, which is 0.025 square. Pi into 0.025 square will be 1.96 into 10 to the power minus 3 square meters. That is the cross-sectional area. So the magnetic flux linkage, or the magnetic flux will be B into A So B is given changing from 0 to 500 millitesla. So 500 into 10 to the power minus 3 to convert to Tesla into the area is 1.96 into 10 to the power minus 3. That is 9.817 into 10 to the power minus 4 Weber. This is a magnetic flux. Okay. When the flux density changes from 0 to 500 millitesla, this is a magnetic flux. So the change in flux linkage will be this 9.814 into 10 to the power minus 4 multiplied by the number of turns, which is 300 turns. So 9.817, no? 9.817. So that multiplied by 300 will give you 0.2945. Weber. These are flux linkage, change in flux linkage. So the EMF induced will be delta N phi over delta T, 0.2945, that divided by 50 milliseconds, which is 0.05 seconds. That is 5.89 or 5.9 volts. Have you got this answer? No, we did that few weeks back about. Okay.
So shouldn't it be 300 into 9.817 into 10 to the power minus 4?
Sorry, come again.
Shouldn't it be 300 into 9.817 times 10 to the power minus 4? Because in
Same thing. Yeah. Okay. Right on the next question. Zoran has a wire coil of 120 circular turns with a radius of 5 centimeters. Let's go down. Right. Zoran has a wire coil of 120 circular turns with a radius of 5 centimeters. With a radius of 5 centimeters. Held in a magnetic field. Held in a magnetic field. With a strength of 20 millitesla. With a strength of 20 millitesla. Full stop. Anyway, you won't be able to see that. I will read it, right? Zoran has a wire coil of 120 circular turns with a radius of 5 centimeters, comma, held in a magnetic field with a strength of 20 millitesla. Okay, full stop. He removes it from within the magnetic field. He removes it from within the magnetic field to a place completely outside the field. he removes it from within the magnetic field to a place completely outside the field. To a place completely outside the field in 0.02 seconds. Full stop. What is the EMF induced in the coil? What is the EMF induced in the coil? Can you give it a try? Done. Done. What is your answer? 0.9424. Let's see. So guys, magnetic flux linkage in phi will be N into BA. N into B into A is pi r square. So N is 120 turns. Magnetic flux density is 20 millitesla, so 20 to 10 to the power minus 3 into pi into r square is 0.05 square. That is 0.0188 Weber. That is the flux linkage after when the strength is 20 millitesla. So they are saying he removes it from the magnetic field. So it was within the magnetic field and then he removes it to a place out of the magnetic field. So the magnetic flux linkage through the coil will change by 0.0188 Weber. So that divided by the time taken is 0.02 seconds, that is 0.94 volts. Exactly right. So when he removes this, during the time he is removing, there will be an average EMF induced 0.94 volts. Is that clear? Yes. Right on the next question. What is the flux, part A? What is the flux linkage if what is the flux linkage? What is the flux linkage? If a square coil with 10 centimeter sides, square coil with 10 centimeter sides, and having 500 turns, interacts with a magnetic field, interacts with the magnetic field, B equals 0.33 millitesla. B equals 0.33 millitesla. Part B. Part B. The coil is turned through 90 degrees. The coil is turned through 90 degrees within the field the coil is turned through 90 degrees within the field, comma, moving from position perpendicular to the field, moving from a position perpendicular to the field to a position parallel to the field. Moving from a position perpendicular to the field to a position parallel to the field, full stop. This action takes 12 milliseconds. This action takes 12 milliseconds. Full stop. What are the induced EMF in the coil? Give a try.
Sir,
Yeah.
so why didn't you tell the 0. Okay, nothing.
I didn't get you.
Nothing.
Okay, what the question says is something like this. So guys, now imagine the magnetic field lines are coming from that side. Okay. So the coil is kept like this. The magnetic field lines are passing through the coil. Magnetic field lines are passing perpendicular to the coil. Okay. Then there is a magnetic flux linkage through the coil. Then you turn the coil 90 degrees like this, and the field lines are passing this way. So there won't be any magnetic field lines passing through the coil now. Understand? It was like this. In this position, the coil was perpendicular to the magnetic field. So the magnetic field lines are passing through the coil. Then you turn it 90 degrees. Then the field is this way, parallel to the coil. There won't be any magnetic field lines passing through the coil. Understand? So initially there was a magnetic flux linkage through the coil. Calculate that. Then after you turn it 90 degrees, the magnetic flux linkage through the coil is 0. So then you know what is the change in flux linkage. So the change in flux linkage over time will be the EMF induced. Okay. Done. Okay. In the angle.
Related to finding the DA mostly.
No, it's when it turns, what you have to understand is flux linkage through the coil becomes 0. So fine. What are the flux linkage? The first one is, what is the flux linkage if a square coil with 10 centimeter sides having 500 turns interacts with magnetic field of 0.33 millitesla. So guys, the area will be, it's a square, no? The area of the coil will be 10 centimeters into 10 centimeters, which is in meters. 0.1 meters into 0.1 meters. So the cross section, the area of the coil is 0.01 square meters. Agree? Then magnetic flux linkage will be, magnetic flux will be B into A. Magnetic flux linkage will be B into A into the number of turns, correct? So B is 0.33 into 10 to the power minus 3. A is 0.01 into N is 500. That will give you 1.65 into 10 to the power minus 3 Weber. Have you got that value? Magnetic flux linkage. Now it's a square coil.
So when they ask us to find the flux linkage, if we find it without the 500 turns, is it wrong?
Yeah, no. If you find it without the 500 means, that means you are just finding the magnetic flux. Magnetic flux linkage means magnetic flux multiplied by the number of turns. Okay.
So magnetic flux applies to only one.
So on, correct. So the next part, the EMF induced will be change in flux linkage over the time taken. So guys, the change in flux linkage will be 1.65 into 10 to the power minus 3. Over the time taken is 12 milliseconds, 12 into 10 to the power minus 3. It's about 0.14 volts.
So but do we have proof that the flux distribution is symmetrical?
Now you have to take it as it is uniform. Uniform. Okay, right. Let's take the tube. Take the tube. Yeah, in a few minutes. Let's start question 2. Question 2. No, before that, question 8. Read the question. Faraday's law can be written as E equals minus dn phi over dt, rate of change of flux linkage. State the name of the term N phi. N phi means what, guys? Magnetic flux linkage. N phi is magnetic flux linkage. State the name of the term N phi. And its unit. What is the unit? Weber.
Weber. So I wrote WB. I didn't write Weber.
Okay, that should be fine. Part B. A coil of 500 turns. Coil of 500 turns and radius 3 millimeters is placed between the two poles of an electromagnet as shown. The terminals are connected to an AC power supply. A coil of 500 turns and radius 3 millimeters is placed between two poles of an electromagnet as shown. The terminals are connected to an AC power supply. The magnetic flux density B, perpendicular to the plane of the coil, varies with time t as shown below. So guys, this graph gives how the magnetic flux density is varying, changing through the plane, through the coil. Now there is a magnetic flux perpendicular to the coil. Okay. So how this magnetic flux density is varying is what given in this graph. The magnetic flux density B perpendicular to the plane of the coil varies with time t as shown below. Determine the maximum EMF across the coil, and it's a 6 mark. Okay. I'll give you 2 minutes. Don't write anything. Just read the question. Think about the question. Just tell me how it can be done. Don't write. Just think about how it can be done. At which point? At which time? 2 seconds. I told you to take 2 minutes. Don't give me an answer before that. Think about it.
But G is what? Magnetic field.
B. B is magnetic flux density. Right. I hope you understood the question. I will ask you a few questions before I start with this. Listen. Guys, now there is a magnetic field passing perpendicular to the coil. Or the other way around. Somehow perpendicular to the coil. That magnetic field is not constant. That magnetic field is changing. Since that magnetic field is changing, there will be an EMF induced across that coil. So we are told to calculate determine the maximum EMF induced across the coil. Now you look at the graph and tell me when the time is 0.005, that is this point. The time is 0.005 at this point. What will be the EMF induced?
0.3. Wait, sorry.
Maximum EMF is at that point, is it? So how many of you think the maximum EMF induced is at 0.005 seconds? Yes. Anyone who thinks the maximum EMF induced is at 0.01 seconds? No. Then tell me, what is the EMF induced when the time is 0.01 seconds? 0. Okay. You are 100% wrong. Now listen to me. Now guys, EMF induced is delta n phi or dn phi over dt. There's dn phi by dt means rate of change of flux linkage. Correct? No? Don't write, listen to me. D n phi means n into BA over dt. N into B into A. N is number of turns, that is a constant. A is number of turns, that is a constant. Those two don't change. So which means I can write this as N into A into dB over dt. The B is the one which is changing here. The magnetic flux linkage changes because the B is changing. Listen to me carefully. Okay. The magnetic flux linkage is changing not because of the number of turns is changing or the cross-sectional area is changing. Magnetic flux linkage is changing because the B is changing. So I can write here E equals N into A into dB by dt, rate of change of flux density. Okay. Now the graph that we have been given is magnetic flux density versus time. The gradient of this graph means what? In a velocity time graph, gradient means what? Acceleration, which is the rate of change of velocity. Velocity versus time graph, gradient means rate of change of velocity. Displacement versus time graph, the gradient means what? Velocity, which is the rate of change of displacement. Okay. In any time, any quantity versus time graph, the gradient means the rate of change of that quantity. If you can plot a graph of your mass versus time over the time, okay, the rate of change of that graph means the rate of change of your mass. If you plot a graph of volume versus time, the gradient of that graph means rate of change of volume. So if you plot a graph of magnetic flux density versus time, the gradient of that graph means what? Rate of change of magnetic flux density. Understood? Now look at this graph and tell me when the time is 0.005 at this point, what is the gradient of the graph? 0. Why? This is the graph, this is a point. At this point, if you sketch a graph tangent here, it is parallel to the time axis. There is no rate of change of magnetic flux density at that point. So at these points that I'm indicating on the diagram, or all these points, you may think that the magnetic flux density is maximum, agreed. But the rate of change of magnetic flux density is 0 at those points. Am I right? So actually at those times, the EMF induced will be 0. Okay. Do you understand what I'm saying? Magnetic flux density is maximum, agreed. But the rate of change of magnetic flux density is 0. Okay. On the other hand, if you look at these times, this one, this one, this one, this one, this one, this one, this point, at these points, the magnetic flux density is 0. But the rate of change is maximum. Because if you look at the graph, those are the points where the gradient of the graph is maximum. The slope is maximum. Understood? Those are the points. The gradient is maximum. So I will just randomly pick one of those points. Anything is fine because the gradient at all those points will be the same. So if I randomly take this fellow, that point, and if I can find the gradient of that, how can I find the gradient of that? Draw a tangent at that point. I will draw a tangent at that point. And find the gradient of that tangent. Okay. So guys, on that tangent, here are my points. I will take this point with coordinate 0.006, comma 0.4. And this point has coordinate 0.01, comma 0. So the gradient will be y2 minus y1, 0.4 minus 0 divided by 0.006 minus 0.01. 0.4 divided by 0.006 minus 0.01. That is minus 100. I don't want the minus sign. I just need the rate of change, the magnitude. So the magnitude of the gradient will be 100. So listen. So the determine the maximum EMF induced across the coil will be, maximum EMF will be, maximum E will be, number of turns is 500 turns. And the cross-sectional area is, radius is 3 millimeters. Cross-sectional area is pi r square, which is pi into 3 millimeters means 0.003 meters, that's square. Pi into 0.003 square into dB by dt, the magnitude is 100, the maximum. So here is my answer, 500 into pi into 0.003 square into 100. $1.41 volts. Okay.
Yes, this looks so similar to a sine graph.
It is a sinusoidal graph.
Like
That family of graphs is you call a sinusoidal graph. Even if you take up the first graph, it is a sinusoidal graph. Even if,
like what I mean is like the starting points, everything's the same as.
yeah, correct. So that is a sinusoidal graph. There are many graphs like that. Not only this. Even if you take the variation of a alternating voltage, it will be a sinusoidal graph.
I guess it-
That is how it is varies.
So our explanation is just.
No, there can be there. If you do go in detail, there are particular equations for every element, which is not completely there. So guys, at one of those points where the gradient is maximum, find the gradient and use this, you will get it. Understood. Wait. Make a note for your reference. Yeah, it's like this. I just took this point. No, I took this point, right? If I had taken this point, I would have got the same plus 100. If I had taken this point, it will be minus 100. If I had taken this point, it will be plus 100. So I just want the magnitude. What are they asking is determine the maximum EMF across the coil. No? So the EMF across the coil is an alternating EMF. So at some points it will be maximum positive 1.41. At some point it will be maximum negative 1.41. So I just need the value. So 1.41. I don't need the sign. Okay. Okay. Make a note for your reference. The EMF induced will be maximum. EMF induced will be maximum at the points where rate of change of B is maximum. Okay. The EMF induced will be maximum at the points where the rate of change of B will be maximum. Is that clear? So guys, learn what you are supposed to learn from this question. This will be tested in many questions. Okay. Understand how to use a graph and find the rate of change of maximum by plotting a graph, by drawing a tangent at the relevant point. Right, guys, for the same question, what if they had given the graph and if they ask you to calculate the EMF induced when the time is 0.042 seconds, what do? Draw a tangent at the point 0.042 seconds and find the gradient of that one and use that as the dB over dt. Understood? So if they ask you to find the EMF induced at a particular point, just draw the tangent at that point and use that as a dB by dt and use the equation and find the EMF induced. Okay. Right, part C. Some electric motor designs rely on electromagnetic induction. A laboratory demonstration of the principle of an induction motor is shown. An aluminum disc is free to rotate and is initially stationary. A powerful magnet is moved around the disc. A powerful magnet is moved around the disc in the direction of the arrow without touching the disc. Okay. A student suggests that the disc will start to rotate as the magnet is moved and that the disc will rotate in the same direction as the movement of the magnet. Discuss this suggestion. We will come back to this a bit later. Yeah, hold on. Right, guys, you can go for a break. See you in 15 minutes. We'll come back and continue.
That's what actually is.
Right, okay. Guys, turn to question number 2. Question 2. A student placed 2 magnets on a holder. 2 magnets on a holder, so that the north pole of one magnet faced the south pole of the other magnet. The arrangement was placed on a sensitive balance, calibered to measure force. The student held part of a closed loop of wire between the magnets as shown in the photograph. The student held part of a closed loop of wire between the magnets as shown in the photograph. When the student moved the wire quickly downwards between the magnets, the reading on the balance changed. Explain how the reading on the balance changed. It's a 6 mark. Read the question again. Did you understand the question? Okay. Right, guys, now there is a top time balance. There is a balance. And on top of that balance, there is a magnet. There is a magnet. Okay. There's a magnet placed on the top time balance. So then the top time balance will be reading the weight of the magnet. Correct? Then what you are doing is you are holding a wire between the magnets, and you are moving the magnet. You are moving the wire quickly downwards between the magnets. Then there's no battery or current or anything involved. You just move the wire down. So when you move the wire down, they are telling the reading on the balance is changing. Explain how the reading on the balance changes. Do you have an answer? Magnetic field gets cut. Very good. Then what happens? Then there will be an EMF induced across the coil. Correct. Then what happens? There will be a current in the wire. Agreed. There will be a force on the. Good. Points are correct. What's next?
The current is shocked the person in
No.
drop.
Don't worry, this current is not going to be such a large current. We are talking about a small magnet. So the current induced will be a microampere or a milliampere current. Nothing will happen to the man. He might not even feel it, okay? So it's an extremely small current. He is not going to get an electric shock. Okay. Fine. It doesn't matter.
Can you say resistance in balance was equal to the current passing through?
Balance won't detect the current. Balance will detect the
Force.
Okay, now you didn't tell me how a force is coming into the picture. You told me, okay, Y is moved down, so it cuts the magnetic field lines, correct? So there will be an EMF induced across the wire, correct? So there will be a current in the wire, correct? I agree up to that point. After that, huh? There will be a magnetic field around the wire. Okay, fine. Okay, then what will happen? Mm. I move wire when you move used to the length used. So so Lenz's law says this: when you try to push the current down, the force on the wire will be upwards due to the EMF induced. When you try to move the wire up, the EMF induced will be in such a way to pull it down. Okay. So now, since you are moving the wire down, as per the Lenz's law, the EMF induced will be EMF induced in the wire will give a force on the wire upwards. Correct? Force on the wire is upwards. Then tell me what will happen to the balance reading. Will it increase or decrease or what? It will? It will? Increase.
Increase
Why?
because so when the force is when there's a force up, there'll be a downward force also.
Correct, very good. So guys, now this force up on is on the wire, right? On the wire, the force is upwards. So it's Newton's third law pair will be the force on the magnet downwards. The magnet exerts a force on the wire upwards. So the wire will exert a force on the magnet downwards. So basically the magnet is being pressed down. Okay. So the magnet is being pressed down means the balance reading will increase. Exactly. I repeat, listen.
Why would the wire cut the magnetic field?
Now there are magnetic. Now they are saying this one is a north pole, the other one is a south pole, right? So there are magnetic field lines from the north pole to the south pole. So there are field lines. You are just moving the wire, cutting that. So the magnetic field lines are being cut.
So whatever you put in between, you get cut from your wire.
Yeah. If you are, it depends on how you are descending it. If it is perpendicular, it will get cut.
If you put a pen on it,
Yeah, it will. Okay, right. I repeat, guys, listen. So the wire is moved downwards, so it will cut the magnetic field lines. So there will be an EMF induced. The EMF induced will be in such a way to oppose the change passing it. So there will be a force on the wire upwards by the magnetic field. So by the wire, there will be a force on the magnet downwards. So that means the magnet is getting pressed downwards. So which means the top band balance reading will increase. Understood?
So you do that.
You are moving the wire down.
Yes.
Magnetic field lines are cut. EMF is induced. According to Lenz's law, that EMF induced will be in such a way to oppose the change you are causing. You are trying to push it down means the force on the wire will be upwards. So force on the wire is upwards means the force on the wire is upwards by the magnet. So according to Newton's third law, the force by the wire on the magnet will be downwards. So the magnet, on the magnet, the force is down means the magnet is what kept on the top balance, right? So the balance reading will increase. Correct? So that will get you the 6 marks. Let's write. When the wires move downwards, come on, it cuts the magnetic field lines. It cuts the magnetic field lines. And there will be an EMF induced across the wire. There will be an EMF induced across the wire, so that there will be a force on the wire upwards according to what? Lenz's law. According to Lenz's law. Full stop. There will be a force on the wire. There will be a force on the wire upwards according to Lenz's law. Full stop. Full stop. So there will be a force on the magnet. So there will be a force on the magnet downwards according to Newton's third law. Full stop. So the balance reading will increase. So the balance reading will increase. I'm not very sure, but to speak about the wire is moved downwards, it cuts the magnetic field lines, and there will be an EMF induced. There should be one for the mark. When the wire is moved downwards, it cuts the magnetic field line. There should be one mark here. And there will be an EMF induced. There should be another mark there too. So that there will be a force on the wire upwards. There should be a mark on that. and mentioning maybe the Lenz's law, there should be a mark on that. There will be a force on the magnet downwards, there should be a mark on that, according to Newton's third law. And for the final result, there should be a mark. Okay. Right. Guys, part B, can you give a try? Part B. You give a try. Okay. Right. Anyone getting closer to an answer? Anyone? Okay, guys, let's look at this. A voltmeter was connected across the ends of the wire, ends of a second wire. The student moved this wire vertically downwards between the magnets of at a constant speed. A potential difference was observed on the voltmeter while the wire was moving. Calculate the maximum PD that could have been measured. Length of each magnet is given 34 millimeters. The height of each magnet is given 20 millimeters. Magnetic flux density between the magnets is given. Vertical speed of the wire is given. Now listen to me. You understand the question, right? Wire is moving, cutting the magnetic field lines. What will be the EMF induced across the wire? Okay. Now look at this. Now, this is one plate, one magnet. This is the other magnet, the other pole. So there is magnetic field lines from here to here. Correct? No? So what is the area of this? Length is 34 millimeters. Height is 20 millimeters. So area of a face is 34 means, guys, 0.034 meters. 20 millimeters means 0.02 meters. 0.034 into 0.02 is 6.8 into 10 to the power minus 4 square meters. That is the area. So the magnetic flux linkage will be, or the magnetic flux will be phi equals B into A B is 0.35 into A is 6.8 into the power minus 4. That is 2.38 into the power minus 4. Weber. This is a magnetic flux. Okay. And now this is moving at a speed of what? 2.2 meters per second. So guys, look at this one. I will use speed equal distance over time. For this wire, speed is 2.2. Distance is 20 millimeters, which is 0.02. Over time taken is t. So the time taken for this wire to cross this will be 0.02 divided by 2.2. It is 9.09 into 10 to the power minus 3 seconds. Now, this is the time taken for the wire to move across this magnetic field. Am I right? You are moving the wire at the given speed and you are moving a distance of 20 millimeters. Correct? So I can find the time taken for the wire to cross the magnetic field is 9.09 into 10 to the power minus 3 seconds. Then by using the EMF induced is what we want. That is the flux linkage cut by the wire, which is 2.38 into 10 to the power minus 4 divided by the time taken is 9.09. Sorry? 2.38. So 2.38. No, this is just a wire, not a coil. Okay. 2.38 into 10 to the power minus 4 divided by 9.09 into 10. I'm getting it at 0.026. volts.
Sir,
Guys, yeah.
shouldn't the area be of the wires and not the magnets?
It has to be the magnetic field lines are between the magnets, right? So I want to know the magnetic flux in that area. So the magnetic flux in that area will be magnetic flux density multiplied by the area. So area for which the magnetic field is there. It is not a coil, it's just a wire which is moving. So it will be the amount of flux cut per unit time, not a coil.
So if it was a coil, we would be calculating the area of the
That is a-
radius. I mean the area of the coil.
That is a different type of question that we did earlier. The magnetic field was passing through the coil. Now here the wire is cutting the magnetic field. It's a different story. Okay.
Okay.
Guys, at the bottom of the page, there is a barcode. If you scan that, you can find from which paper this question is. Always, you can check the marking scheme and see whether the answer is right or the marks are allocated for what you can check. You can install a barcode reader in your phone. It is free of charge and app. Okay. There are enough barcode readers. Just have one of that. I have one called Q Reader. You can just open it and scan it. It will show you the code from which paper this question is. It will take you to the paper. Okay.
I didn't realize that the distance was the height.
It's moving this way. So that is the distance.
So I knew that where is was DOT, but I was stuck at what
The distance is. Right. Let's then turn to And next week we are starting with a new topic. We will do more questions from this, but after that we will be starting a new topic next week. Question 16. 16. Very similar to the earlier question that we did. Guys, don't write. I will give you an answer, but I want your input. Read the question. A student carried out an investigation of Lenz's law. A copper tube was suspended from the force meter, as shown. A magnet was released at the top of the tube. A magnet was released at the top of the tube. When the magnet was falling through the tube, there was an increased reading on the force meter. The force meter is showing a high reading. Explain why there was an increased reading on the force meter. So guys, this force meter, originally, this copper tube is what hanging on the force meter. Originally, the force meter will be showing the weight of the copper tube. Correct? And now when the magnet is falling through the copper tube, the reading is increased. Can you give me reasons? Step by step. When the magnet is falling down, it will cut the magnetic field lines. Okay? So there will be an EMF induced in the copper tube in such a way which opposes the change causing it. So now the change causing it is the magnet which is falling downward. So there will be an EMF induced in such a way, there will be a force on the magnet upwards. Am I right? There is an EMF induced because the magnet is falling. It says what? Always there will be an EMF induced in such a way to oppose the change causing. So there will be an EMF induced in the copper tube to oppose this. So the magnet falling is what causing it, means the EMF induced will be trying to stop that. So that means the force on the magnet will be upwards. So force on the magnet by the copper tube is upwards, means force on the copper tube by the magnet will be downwards. So that means now the copper tube is like being pulled further down, not only by the gravity, but also due to the fall of the magnet. So which means the force meter reading will be increased. Okay, very similar to the previous question that we answered. Exactly.
So wherever there is a magnet, it induces electromotive force.
If it is moving, just stationary means nothing will happen. Today we, at the very beginning, that is what we learned. The first thing that we learned today is that's EMF induced. Okay. Right. So guys, write an answer. As a magnet falls, the magnetic field lines will be cut by the copper tube. As the magnet falls, the magnetic field lines will be cut by the copper tube. And there will be an EMF induced. In the tube, as the magnet falls, the magnetic field lines will be cut by the copper tube, and there will be an EMF induced in the tube. Full stop. According to Lenz's law, the EMF induced will be in such a way to exert a force on the magnet upwards. According to Lenz's law, the EMF induced will be in such a way to exert a force on the magnet upwards. Full stop. According to Newton's third law, there will be a force on the tube downwards. Full stop. So the reading on the force meter will increase. Okay. Right. Guys, then guys, question number 17 part B, I have already asked you to do for homework, but we haven't discussed in the class. So we will do that. If you haven't done it, complete it. 17 part B and C. 17 part B and C. And 20th one we have to discuss. And try question 22 for homework. And 27th for homework. 27th. And 28th for homework.
So when you say and, it means the last part, right? Or this you say or, and then you say and last. So that means
Okay.
28 is the last.
29th and comma.
So
29th. 30th. And that's it. So we will discuss this and we will start with a new topic next class. Bye people, have a nice weekend. See you next week. You're welcome. Bye. Bye. See you.